Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. It is February 6th, 2019, and I hope that everyone is having a very fine week so far. And I'm excited to present to you all today. This webinar is being recorded, so for those of you who are listening in, you will be sent a link to where you can watch the recording again later, or you can forward it around to your colleagues. For those of you who are listening in to the recording later, thank you for joining us. I have included my presentation slides for this webinar today as a handout. So if you are listening in live, you have access to that information. If you are joining in on the recorded version and you would like to get my presentations, please feel free to email me directly at benkeiser@aft.com. That's BENKEISER at aft.com, and I will be happy to send it to you. As usual, I typically always show the majority of the content in the software itself, but this presentation has a few talking points on the slides themselves, so there'll be a little bit more in the slides here than I usually do. Okay, let's go ahead and get started. I'm going to be talking about how you can do a Waterhammer analysis with AFT Impulse 80% easier by importing your model from AFT Fathom, and we'll see what that looks like. So before we get started, just a couple of quick notes that I want to make is AFT Impulse version 7 is now available. It was released late November of 2018, and it contains a lot of powerful new features and capabilities that you'll enjoy being able to use. And so you can download that from our website, and you can also access the new features list on the product page. That way you can read about all the new features that we incorporated into AFT Impulse 7. Next thing I want to discuss really quick is that right now we are running a very special promotion where if you already have AFT Fathom, then you will get 10% off of AFT Impulse until March 31st, 2019. So make sure that you take advantage of that here quickly. Again, if you have Fathom, you'll get 10% off Impulse. If you don't have Fathom yet, you can get Fathom and Impulse together, and you'll also receive 10% off of that. So be sure to mention this promotion, and you'll be able to enjoy that discount. And this is where you can find more information about it. Just a quick highlight of our main AFT products. We have AFT Fathom for steady state modeling, AFT Impulse for gas flow modeling, and AFT, or might have said it, I meant AFT Aero for gas flow, compressible flow modeling. And then Impulse is for Waterhammer, and it's for liquid piping systems. I'm not going to spend very much time going through each individual product and what they do. I will refer you to our website where you can find that information. So if you go to aft.com, to our website, under the products menu, you can read about each individual product themselves, or you can get an overview of what all of them do from the overview menu, and just hover over any of these and it'll show you some additional details. And for some reason my computer is not working. I don't know what's not showing the icons, so hopefully my computer will get fixed in a little bit here. All right, let me drag this back off to the side. All right, so what's the difference between AFT Fathom's XTS module and AFT Impulse? AFT Fathom has a extended time simulation module to be able to use, and you can access it when you run AFT Fathom. Simply check the box right here, and that's how you can turn on the XTS module. And XTS allows you to do transient flow modeling in AFT Fathom. And I mention that because Fathom is primarily a steady state flow modeling tool, and then Impulse is where you would do transient modeling. So you can do a dynamic or transient modeling analysis in two different ways. Fathom, again, is a steady-state full modeling tool, and it has the XTS module that allows you to do transients. And then AFT Impulse is all about transient modeling. So how are these two transient flow analysis options different? When do you need AFT Fathom with the XTS module versus AFT Impulse? Well, that's exactly what we're going to talk about today. So the best way to think about when you need Fathom XTS versus AFT Impulse is to think long-term versus short-term. If you're doing transient modeling with the AFT Fathom XTS module, that's a long-term transient simulation. Don't be confused by long runtime. It's long-term simulation. So your simulation periods are several minutes, hours, maybe even days. Perhaps you might want to see what happens to the system if you know how the flow demands at different points change throughout a 24-hour period. And so that would be a long-term transient simulation. And that's what Impulse will capture, is how your system dynamically interacts with itself over the long term. A key assumption I want to point out when you are doing transient modeling with AFT Fathom XTS is that every time step is at a steady state operation. What we mean by that is we're simply doing the Newton-Raphson mass balance, and we're assuming that all flow is steady at each time step. So what this is meaning is if you have a long period of runtime where your time step is on the order of a couple minutes, maybe 5 minutes, 10 minutes, if you're going, from one time step to another and they're separated by 10 minutes apart when you're taking data, perhaps that's a very valid assumption where you could know that at each time step you're at a steady state operation. Things are changing very, very slowly throughout the simulation. The reason why I mention that is because if you're changing that slowly in your system, then that would indicate that perhaps all of your pressure and velocity waves that would propagate through the system have fully dampened out with each time step. And so that's a very key assumption to pay attention to when you're modeling with AFT Fathom XTS. If you're using AFT Impulse, that's a short-term transient simulation. So the simulation periods are very short in Impulse. You're typically going to be looking at what happens 10 seconds to maybe 30 seconds after a sudden event, like a valve closure or a pump trip or something like that. You might model out to what's happening a minute or two after an event, or maybe a few minutes at the most. But overall, what you want to see is what's happening in that very short period of time during a sudden pressure surge event. And you need very fine resolution to be able to capture what's happening in that time. And so in order to capture what's happening, you need AFT Impulse because it will account for the wave speed as the pressure and velocity waves propagate throughout the system. Another reason why you're only looking at maybe 30 seconds to a minute on average with AFT Impulse is because if you have a sudden pump trip or a valve closure when things go wrong during an emergency situation, maybe you have a couple of minutes to do something about it. So that's why with Impulse, you're only looking at those shorter periods of time. So overall, AFT Fathom and AFT Impulse are two different ways of doing a transient simulation. Fathom XTS models slow transients, and as you can see here, this is a screenshot of the transient control window in Fathom XTS. This is where you specify your start time and your stop time. So for this particular screenshot here, I am running the simulation for 120 minutes, 2 hours, and my time step is going to be 1 minute. So I'm neglecting anything that's happening from 1 minute to another. And again, that might give your pressure and velocity waves enough time to dampen out when you're going from 1 minute to the next. On the other hand, AFT Impulse captures fast transients. And so one thing I want to highlight here is with Fathom XTS, the number of time steps here is 120. So you're going to have 120 time steps for your simulation. Impulse, the transient control is a lot more difficult. There's a lot more information in here that you can specify. Essentially, the base information that you're specified is the same, start time and stop time. But look at the difference in the time step. The time step for an impulse simulation is on the order of several milliseconds compared to several minutes or hours or days with AFT Fathom XTS. Also, look at the difference between the number of time steps with XTS versus AFT Impulse. Why is this? It's because your typical wave speed of a fluid in a piping system is on the order of several thousand feet per second. So the amount of, if you have a sudden valve closure that sends a really high pressure through your system, the amount of time that it takes for a pressure wave to reflect all the way back to a tank and then back to the valve is a very, very short time frame because the wave speed is so fast. Things propagate through the liquids really, really quickly, and that's why you would use AFT Impulse for that. So what types of questions would AFT Fathom XTS help with? Here are some examples. How does the system change over long periods of time? How do the control valves respond if you're changing from one operation to another? So maybe you're not doing a sudden valve closure or a sudden pump trip, but maybe you have a control valve where it's operating initially at 1,500 gallons per minute, and you want to change that to 2,000 gallons per minute. And maybe you're changing your control valve set point over a minute or so, and then you want to be able to see how the system dynamically interacts while you're making those changes. Another example is how are the pumps operating on the curves as your flows change throughout the day? How long does it take for your tanks to drain or fill over time? That's a wonderful advantage of using Fathom XTS. Is because with Fathom XTS, your reservoirs can be able to be a lot more sophisticated and model actual finite tanks, either open tanks or closed tanks, and that's how you can track the liquid height change over time. As one tank drains, when would a standby pump come online to start filling it back up? What causes a valve to close? Do we achieve the desired liquid height in our tanks? Or does the valve close because one of the tanks is about to spill over? So that's an example of some of the questions that AFT Fathom XTS module would address. How about AFT Impulse? Impulse, you're going to be trying to figure out how high do the pressures get if a valve slams shut all of a sudden? Or where does cavitation happen in your system? And what are the pressure magnitudes when your vapor bubbles collapse? What happens to your system pressure during a pump trip? How do your check valves, relief valves, and control valves respond during a sudden event? Do they function properly, or do you have a lot of chatter going on in your system? What types of surge suppression equipment would be needed to protect in a sudden surge event? So all those are types of questions that you'd be asking with AFT Impulse, which are different than what you'd be asking with the AFT Fathom XTS module. So now I'm going to jump into the software and show you what you've been waiting for this whole time. So I'm going to start with a simulation in AFT Fathom XTS. And what we have here is a situation where I am pumping water to two separate delivery tanks. So I've got one tank at a certain elevation, and I have another tank at a different elevation, just to make the model slightly complicated. And my tanks are initially empty. So I'm going to fill up the tanks over time. I have assumed a 150 square foot cross-sectional area. I can't remember what the diameter of the tanks were off the top of my head. I think either I assumed 20-foot diameter tanks or maybe 10 feet. You can do the math. It just asks you for what the cross-sectional area of your tanks are if you're using Fathom XTS. So here's what I'm going to do is we have two operating tanks where I have both tanks initially empty, and in case one, we need to get each tank's liquid height up to 15 feet in the discharge tanks. In case two, we need 20 feet. Now, in this particular model, I'm using a new feature in AFT Fathom XTS, which also exists in AFT Impulse 7, which is incredibly powerful and useful. It's called multi-condition events. If you were to define an event for a particular transient, there is what's called a multiple condition event option, and I'll show you what that looks like. The reason why you would use a multiple condition event is so that you can model and or logic. And so here I have two different logical situations that can happen. Is in one case, I have where my discharge tanks are too high. So my discharge tanks where they're too high would be 25 feet. However, let's say that my desired tank here is 15 feet. So what I could do is I can tell that valve to shut off if either the discharge tank or the liquid height in either discharge tank is too high and about to spill over. That's one reason why I'd want my valve to close. Another reason is if both tanks got to be the same or the required liquid height. So I've got or logic, and then I have and logic right here. So some questions that I want to ask for this model is, when does the valve close? What causes the valve to close? Is it because my liquid heights are too high in one of the tanks, or is it because I get the right height in both tanks? How do the liquid heights change over time? How does the flow to the pump change over time? How does the pressure of the valve change over time? So those are the things I'm going to ask with this specific example. So now I'm going to go ahead and jump into AFT Fathom here. So I'm going to move my PowerPoint to the side here. And give me one quick second. Let's see. Okay, so here's my system, and I have a 30-foot liquid surface elevation in my supply reservoir. So my supply reservoir here, it's a finite reservoir. So the first question is, how do you turn on the XTS module for Fathom? One way is you can go to the Tools menu and then click on Activate Modules and simply check the box here. Or you can click on the button next to the status light, and that's also where you can turn on the XTS module. So when you turn on XTS, your reservoir window changes. Your reservoir window allows you to not only model infinite reservoirs, which is the default, and steady state Fathom is what you would do with that. You can also model finite open or closed tanks. So my supply reservoir here is infinite. I have a pump curve where I've got my head versus flow, my MPSH curve, my efficiency, and then I have my valve downstream of the pump. My valve is at an elevation of 200 feet. And then I have my discharge tank number 1, where my cross-sectional area is 100 square feet. It's initially empty, so my liquid height at the bottom is 0. And then I've also defined the elevation accordingly. So the bottom of tank elevation is 210 feet, and that's also where my pipe is going to be connected. One tip that I have for you is if you are using AFT Fathom XTS, it's a good idea to connect your pipes to your tanks in terms of elevation, not depth. The reason for that is because this liquid height can change. And as that liquid height changes over time, if you were to choose depth for your pipe connections, then that would mean that your pipe is moving up and down as well, which is not correct. So make sure that you use pipe elevation to reflect reality more closely. Finally, my tank liquid height is 30 feet tall. So I've got a 30-foot tank there. I don't want my tank to overflow. My second discharge tank is similar, but the bottom of that tank is at 215 feet, and it's also a 30-foot high tank. So I have some slightly different piping in this pipe than I do for this pipe. Now, here's how I went to go set up my multiple condition event. So in this scenario here, I have my valve, and my valve is going to close based upon some sort of criteria. Let me back up really quick to my base scenario. If I go to my base scenario and I go to the valve window here, we have 4 different types of transients that you can model in Fathom XTS. There's time-based transients and event-based transients. Time transients will cause this profile to function relative to when your start time happens of the simulation. However, if I am instead doing a event transient, then this transient profile, which dictates how my valve will close or open over time, only will happen if this event criteria is satisfied. So in order for an event transient to happen, the criteria has to be triggered. So let me cancel out of that, and I'll go to my multi-condition scenario. So what I'm showing you right here in Fathom XTS is a bit more advanced. So I would expect that you wouldn't just be jumping off into doing a multi-condition event like this to simulate the and or logic for the valve. It's a bit more tricky. So what I would recommend is if you are wanting to work with AFT Fathom XTS, go to the help menu and then show examples. And then you can open up the examples help file. This contains all of our walkthrough tutorials for all of our examples here in Fathom. And then here's the Fathom examples area. So here we have several tutorials that will teach you how to use the XTS module for doing transient modeling in Fathom. Even if you do not have a license for XTS, you can still read these examples to learn how it works. So I would recommend if you've never used Fathom XTS before, start there. After that, if you want to get into the more sophisticated modeling like using and or logic, just go to the main help file, and then you can do a keyword search for multi-condition. And that's where you can learn about how to model multiple condition events and do the more sophisticated transient modeling with and or types of logic. So here's what I'm doing here. I have 2 different cases where my valve could potentially close. One case is I want my valve to shut off if either tank gets to be too high. So if the liquid height gets to be a certain level in either tank, that's one reason I'd want the valve to close. The other case is if I get the correct height. So if I get the correct height in both tanks, then that's the other reason that my valve would close. Now, again, start with the basics in the examples tutorial because this can be a little bit tricky when you're trying to do the transient modeling. So if I open up my multiple condition event window here, I have 4 separate cases. I have my discharge tank being too high for tank 1, my discharge tank too high for tank 2, and I have my desired tank height for tank 1 and tank 2. So if I click on any of those, you can see what the requirements are. So here, if for my discharge tank being too high, that's 27 feet. So if the liquid height in either of these tanks gets to be higher than 27 feet, that's where I want my valve to close. So that's where I have shut off the valve too high. That's a new multi-condition event that I added. I added my 2 conditions and I choose the or type of logic. So if either of those has liquid heights that are too high, above 27 feet, close the valve. Now, For the desired liquid height, in one particular case, I need 15 feet. So I've got 15 feet as my requirement for my liquid height that I need. And in that particular case, I would want my valve to close if both of my liquid tanks achieve a height of 15 feet. So that's why I'm using AND logic. So I'll shut off the valve correct height. I'm going to require that both tanks achieve 15 feet. That's when my valve would close. And then I would just have to add in one more event right here, which is shut off the valve on too high or just right. And so that's where you would have essentially multiple condition events for the individual and or logic. And then I would have a multiple condition event for the multiple condition events. All right. So here's my first case. I want my desired liquid height to be 15 feet. So that's this scenario here that I'm going to load. So I want to make sure that this is set to use my multi-conditions to where these are 15 feet for the required liquid height. And in my transient control, so I've got time simulation, I would do transient and then transient control. So my start time is at 0, my end time is at 120 minutes, and I'm doing 1 minute increments. And I'll run the model. So again, the first question that I want to look at is, when does the valve close? So as this finishes running here, one thing that I have done is I've created some design alerts. So I'll go to the output window here, but I want to go back to the design alerts really quick. So one thing that I did is I went to the tools menu and then design alerts, and I created 2 design alerts right here. So I have 2 design alerts, and this is going to flag my attention if my liquid height gets to be above 27 feet for either of my discharge tanks. So this is really useful for being able to figure out if your liquid tanks are getting too high and they're about to spill over. So I created a design alert for that. So my first scenario here for 15 feet being my desired liquid height, I do not see any design alert violations in my output window. So that's good. So the question is, when does the valve close? Well, the easiest way to answer this question is by the event messages here. So when I look at the event messages, my valve closes at 93 minutes. Now, how do I know that my valve is closing at the correct time? Well, what I can do is go to the graph results window. And what I have done is I've already pre-created a couple of graph list items. So this is a graph list item where I have plotted on the transient tab for reservoirs. I'm plotting the discharge tanks liquid height, and I'm cross-plotting the design alert right here. So I've already set that up. When you set that information up and you plot your graph, if you click on this button, that's what you can use to file it away to your graph list manager. That way, you only need to create your graph and set the parameters once. That way, you don't have to reset your parameters every single time you want to see that graph. Only need to do it once. So let's take a look at what's going on right here. I have my design alert. So 27 feet is my threshold. I don't want either tank's liquid height to go over 27 feet. So if either of the liquid heights in either of those tanks crossed my 27-foot liquid height, then that would be the reason that the valve closed. As you can see here, when I'm plotting the liquid height for both of my discharge reservoirs, neither of them are crossing that 27-foot threshold. So that's good. I'm not about to spill over. Now, if you look closely, though, what I can do is I can turn on my rangefinder, and what I'll do is I will follow my red line. That's me. That's my discharge tank height for this reservoir on the left. So as I go along over time, you can see how the liquid height gets higher and higher and higher. And then here is 15 feet for the first tank. So it takes about 49 minutes right here for my tank on the left-hand side to get to my desired liquid height of 15 feet. Now, that liquid is going to continue to fill up that tank because my valve is still open. And the reason for that is because my liquid or my tank on the right-hand side is still filling up. So if we track how long it takes for it to fill, we can see here that this is the time when your tank on the right-hand side gets to be right above 15 feet. So it's 93 minutes. 93 minutes is when my liquid height gets to be 15 feet in the second tank. That's why my valve closed. So when does the valve close? 93 minutes. What causes the valve to close? It's because both of my tanks are above 15 feet. That's my desired liquid height for the tanks, but neither of them have overcome the 27-foot threshold. So that's good. Now what I want to do here is I want to note what my liquid height is in each of those tanks at 93 minutes. So I'm going to go to the output window, and then on my reservoir transient, I'm going to hide my pipes, and I'm going to expand this reservoir. So this is my tank 4, and this is the data for all of tank 4's data points. So if I right-click on a column here, on any of these columns, you can do a quick graph, and that's how you can see the liquid height in one particular tank there. So that's really useful. So I'm going to scroll down here. 93 minutes, my liquid height is at 25.38 feet. So I'm going to write that down. So I've got tank J4, the liquid height for my 15-foot case, I have 25.38 feet. So I wrote that down on my little notepad. And then for tank 6, if I go down to 93 minutes, my liquid height is 15.01 feet. So tank J6 is 15.01 feet. The reason why I'm doing this is because when I bring in my model into Impulse to do a Waterhammer analysis, I know that that's the time when my valve is going to slam shut. So the reason why I needed those two values is because those are going to be starting points in Impulse for my discharge liquid tanks, and that's going to be my start time. So I'll have my liquid heights known, and then that's when I'm going to close my valve. So that's why I wrote down those two values. Now, another question that I wanted to ask was, how does the pump flow change over time? Well, if you simply go to the pump transient tab, you can expand this here, and you can do a graph, and you can see here how the pump decreases in flow a little bit over that 91-minute period until my valve closes. And once the valve is closed, you have no flow through the system. So that's what your pump flow looks like. Last question is, how does the pressure of the valve change over time? So if I go to my valve transient, let me close this. If I go to my valve transient, what I can do is I can go to my output control window here, and then for valves, I'll add inlet pressure and outlet pressure. All right. So if I expand this, my inlet pressure looks like that. So when my valve closes, the deadhead pressure is right above 120 psi. So I'm going to write that down. Valve inlet is 120 psia. And why did the outlet pressure not get added? Let's see, that confuses me. Oh, I went to the wrong tab. So let's see. Valve transient. Okay, so now if I look at my valve outlet pressure and do a quick graph, I can see that my max pressure is just over 32 psi. So that's my maximum pressure. My minimum pressure is 23 psia. So max, and then let me write down my minimum pressure. So minimum is 23 psia. And my minimum input pressure is about 47 psia on the outlet of the valve. Okay, so that is my first case where I wanted 15 feet in both tanks. Now, let's go to my next scenario. My next scenario here, I needed 20-foot liquid heights in both tanks. So here, I don't need 15 feet. I actually need 20 feet for whatever reason. So now all I need to do is go to my valve. And for my valve, I'm going to go to my transient. And then I just simply need to change this to be 20 feet for my desired height in tank 1. Change that to 20 feet for my desired height in tank 2. And update. Click OK. Click OK. And I'll run my model. Again, I'm running it for 2 hours. Now, I'm doing it the poor man's way where I was writing down specific results. While this is running, I want to show you a tips and tricks blog that would be really useful for this situation. So if you go to tips and tricks here, the article that I want to refer you to is on page 2, I believe, and it talks about the brand new Excel Export Manager, which is this blog right here that Mr. Scott Lang wrote. And so this will teach you how you can use the Excel Export Manager to send specific results to a spreadsheet. So rather than me sitting down here with my pen and my legal pad, writing down the results for my liquid heights as well as my maximum and minimum values for my pressures, instead, I can set up my Excel Export Manager to automatically send that data for me into a spreadsheet. That way I wouldn't have to write it down, and I can make life a little bit easier for myself. So be sure to read through that blog article. It'll give you some really good tips and teach you how to use the Excel Export Manager. All right. So let me go ahead and click on Output. So here, what time does the valve close? Well, first of all, we see immediately that we've got a design alert. The liquid height is above the maximum design alert for at 27 feet at junction 4. So my tank on the left, at 101 minutes, that's when that tank height gets to be greater than 27 feet. So if I go to my event messages window, my valve closes at 101 minutes. So it's open for 8 more minutes than it was in the previous scenario where I only needed 15 feet. So now if it's 101 minutes, what do my liquid heights get to be? Well, if I go to my graph results window, I can reload this graph right here. Looks like I didn't double click it well enough. Looky here. This is where you can see that the tank on the left-hand side crosses the design alert threshold of 27 feet. Now, how high do these liquid heights get? If you track along, you can see that your tank on the left-hand side does get to be 20 feet, obviously. It gets to be 20 feet at right around 70 minutes or so. So at 70 minutes, that's when your tank on the left gets the required height of 20 feet. However, the tank on the right-hand side is not there yet. So if we keep going along here, we can see that the tank on the right-hand side never gets to be our desired 20-foot liquid height. So the valve closes before my second tank can achieve the required liquid height. So I don't know, I find that a little bit interesting. And so you can see how a very simple system like this can be really complicated. And this is why the XTS module is so incredibly useful, because you would have to do a whole bunch of steady state scenarios to be able to get this type of information by hand. And XTS completely automates this process for you. You don't have to do any external calculations in Excel for your transient modeling. Just use XTS. It'll dramatically streamline your process. So now what I need to do is I need to go back to my output, and I need to see what my values are. So if I go to my reservoir transient, what I want to know is what are my conditions at 101 minutes, because that's when my valve closes. So at 101 minutes, my tank on the left-hand side is going to be 27.15 feet. So that's this value right here. And then if I collapse this data here and expand this one, go down to 101 minutes, this is going to be 16.63 feet. So again, this is going to serve as my starting point for the valve closure, which is going to be a sudden valve closure in Impulse. And then let's take a look at the maximum and minimum value. So if I go to my valve transient, looks like I need to add on my outlet pressure here. There we go. So here, my maximum pressure on the outlet of the valve is also 120 psia, while the minimum is about 47. That's the same as before, doesn't surprise me. And then the downstream side of the valve is again 23, or it gets up to about 33 on the downstream end for the max pressure, and 23 on the upstream end. And then here's where you can see how the pump flow rate changes over time. All right, so we've finished answering these questions for the steady state case. So we know all of that information. So now that we've done our XTS over the long period of time, figuring out how long it takes those tanks to fill up, we want to do our Impulse example now. So for Impulse, we're going to import the Fathom model into Impulse. So in order to import, you just go to the File menu and then click Open, browse to the folder where your Fathom model is located, change the file type to All, select the Fathom model to open it in Impulse. The majority of all your data is going to immediately get transferred. Some data might need to be slightly modified. For example, your elbow junctions in Fathom get converted to general components of the K factor in Impulse. That's another discussion for another day. And then Impulse will also try to combine pipes and simplify the model upon import. It's very important to do that, but probably best to combine the pipes in a child scenario. So just about all your steady state data should be fully defined. So all you would really need to do in Impulse is define your transients, section your pipes, and do your transient control. So these are the questions that we want to ask for the impulse example here. Uh, uh, so I know what my liquid levels are in the tanks, which triggered the valves to close. What happens when the valve closes? What are the system pressures? Is there cavitation? How does the pressure of the valve change? Does that compare with Fathom XTS? Should we continue to operate a pump against the closed valve? What happens if we try to trip the pump? So those are all the questions that we're going to ask and answer with Impulse. So let me go ahead and I will load my 15-foot scenario case, and I'm going to save my model. I'm not going to close it. I'm going to do File, Save As, and then I'm going to call this for Impulse. The reason why is so I can open up that model in Impulse. So here I am in Impulse. I'm going to go to File and then Open. And then I browse to the folder where my model file is saved. So that's in the Fathom to Impulse webinar. Here's where you need to change your file type. You could change it to just Fathom models, or you could do all models. That way you can open up arrow models in Impulse as well. I'll just simplify it and use Fathom here. So this is the model I'm going to import into Impulse. So I'm going to remove the lock. Yes, I'm going to convert it to an Impulse file. Now, this is a key piece of information here. It's telling me that it's trying to update my fluid in Impulse, which is different than in Fathom. Well, the reason why it's different is because in Fathom, the bulk modulus of your fluid is not required, but it is required for Impulse for your wave speed. So what Impulse is trying to do is it's trying to update your fluid information from Fathom. That way it can include the bulk modulus for your Waterhammer analysis here. So I'm going to click yes, update my fluid from the database. Yes, I'll rename the file. And perfect, here we are. So I'm going to go ahead and jump to my 15-foot desired liquid surface elevation. If we go back into Fathom, how long did I take to close the valve? Well, I closed it linearly. Oops, let's see. I closed it linearly in 30 seconds. So 30 seconds is how fast I closed the valve from fully open to fully closed. And so that's my profile for Impulse. So what I'm going to do here is I'm going to open up my valve window. And this time, instead of using a multi-condition event, I'm just going to do a very simple time transient. Because here I know how fast my valve is going to close. I'll just change that to 60 seconds. So it closes really quickly. And again, I don't need to do the whole 120-minute simulation I did in Fathom. I only care about what happens immediately when the valve closes at that time in Impulse for maybe 60 seconds to a couple minutes. So here I'm closing the valve in 30 seconds from the beginning of the simulation. Now what I need to do is I need to update these two tanks with their proper liquid heights. So if I open up J4, I need to specify my actual liquid height, which is not empty anymore. Okay, so this is non-zero, and for this tank here on the left-hand side, this is going to be 25.38 feet. That's because this is how high the liquid height was, which caused when the valve was triggered to start closing. So this is my starting point for my liquid height right here. That's the only change I need to make for that tank. And then this tank here is going to be 15.01 feet from the bottom of the tank. So those are my two inputs that I need. Now, if I click on the status light to open up the checklist, what we see here is the first three green check marks are completed. My solution control, my fluid properties, and the input for my pipes and junctions. So before I do my Waterhammer analysis, it is a good idea to go to the analysis menu, and then for transient simulation or time simulation, just set that to steady state. So if I run this, in steady state and I compared all of my results that I see right here, I should see these same exact results as I would in this scenario here for my pipes. So if I open up my pipes and I change my scroll bar to 93 minutes, which is right there, 92 minutes. You know what? I might be looking at. Let's see. I might need to rerun this scenario. This should not say 0, of course. It should have actual values in those cells. What happened was in Fathom, when I did my 20-foot discharge height, I changed my multiple condition event. So I have to go back in here, set my multiple condition back to 15 feet, rerun the scenario, and then look at my results. So my results got wiped out. That's why it was showing 0. But essentially, if I compared these results from Impulse with Fathom XTS at a time of 93 minutes, they would be identical. You would see exactly these same values. So that's your starting point. So now when I go back into Impulse here and I change my time to use Transient, you have 2 additional things that you need to do before you run your simulation. Is you would need to first section your pipes. So this is where you break your pipe up into bits so that the transient mass and momentum balance equations can be solved with the method of characteristics. So here my time step is 3 milliseconds. So if you look right here, you see 3 milliseconds, and that's a very, very fast wave speed. As you can see, the wave speed here, right around 4,400 feet per second. So those waves are passed into that system very, very quickly. This is why you need Impulse to be able to track that wave propagation. So Impulse is breaking each of these pipes up into bits. The reason for that is because when this valve slams shut, the pressure, flow rates, and velocities at this station at a certain time step are going to be different than this station. So that's one reason another way how Impulse is different than Fathom XTS. So I sectioned my pipes. Next thing we're going to do is specify my solution control. I'm going to run my model for 90 seconds, so a minute and a half. In a minute and a half, look at this. I've got 40,000 time steps, 40,000 data points for each pipe station throughout my model. So here, all my pipes are broken up into bits. If I save all the intermediate stations, I've got 40,000 data points for each intermediate time step there. So I click OK, and rather than saving every time step, I'm going to skip some time steps here, maybe every 10 time steps. So that way it'll shorten my runtime down a little bit. Okay, so now this is all ready to run. I'm going to go ahead and run my model. And this will finish running nice and quick. All right, so let's take a look at what's going on here. The first thing that we want to look at when we're doing an impulse simulation for Waterhammer is our maximum and minimum results. So if we take a look here, we see that our maximum pressures are really, really high. The maximum pressure in the system, 332 psia. Now, the question is, where is that happening? It says it's happening in pipe 2. Where is pipe 2? Pipe 2 is right here. Well, it tells you what station that's happening at. So here, this maximum pressure is happening at station 41. So I'm going to add a little bit more detail right here. all my pipes are broken up into bits, and in pipe number 2, there's several stations. So if I go to the output control window and format an action, I can show my detailed maximum minimum values. So if I scroll down, here is station 41. That's in the middle of the pipe. And so here is the outlet of the valve, 289 psia. So if you look at the valve outlet, 298 psi is the maximum pressure. What was the maximum pressure in Impulse? The maximum pressure, in Fathom was 120. Well, what's going on here? I can right-click on the valve, and I can generate a plot of my pressure at the inlet of and the outlet of the valve. So a significant difference between Fathom XTS or Fathom and Impulse is in Impulse, you are doing you're analyzing what's happening in your system with graphs. So here, what we see is in 30 seconds, this is when the valve is fully closed. And so this is how high the pressure gets. So what we see here is at this particular point, the pressure actually gets up to 135 psia when the valve closes, not the deadhead pressure of 120 psia. Now, why is this oscillation happening? This is because the pump is deadheading against the closed valve. So if I go down to my pump right here and I plot the pressures at the pump, you can see here how we are deadheading the pump over time, and we're going to start having some problems. So we're just packing up that pressure in that pipe. We don't want that to happen. Now, one thing that you're also going to be doing in Impulse is animations. So I'll select this flow path here, and what I want to see is how the pressure changes in that entire flow path over time. So if I select that flow path on the workspace, I can go to my graph results window. I'm going to do a profile plot. So here I'm going to select the workspace pipes that are selected. Let's look at the pressure as well as the vapor volume, because I want to see if we have cavitation. So when you do an animation in Impulse, this shows you how things change over time. So if I run my model, my valve starts closing, and if you pay attention in the bottom right-hand corner, this is the time frame. So time is stepping forward what looks to be very, very slowly, but we're not even at 2 seconds into the simulation yet. Now, here's something that is important, is that nothing changes for the first 25 seconds or so. Things change very little as your valve closes. That's because the valve does not start to really respond until it's almost closed. So that's when you really start to see a change in pressure. So here, let's take a look at what's happening from 25 seconds into the simulation until after my valve closure. J2, this is where my pump is. So as I continue to run my scenario, you can see how the pressure increases. My valve is now fully closed. So when my valve is fully closed, you can see how that pressure oscillates between the valve and the upstream part of the system. We also have some oscillations down here which are pretty small. Now, as you can see, for whatever reason, this particular system does not have very significant pressure surges, and they're not very large. So that's good. But we haven't looked at what's going on over the whole period. And so we need to keep moving forward in time. So now we can start to see how these oscillations are getting larger and larger. The reason why this is happening is because we are deadheading that pump against the closed valve, and the system is just becoming more and more unstable. So this just shows you that you don't want to be operating your pump when you have a closed valve, this is what the system pressure would look like. So what I would do then is I would trip my pump. So now I'm going to create another child scenario, and I'll call it pump trip. So now if I go into my pump, what happened was I had reverse flow. If you remember that warning message, the warning message told me that you have reverse flow through the pump. So you're not going to have an accurate pump prediction in those circumstances. We're just going to be using the deadhead pump value at that time. So here, you'd want to include a 4-quadrant data set to better capture what would happen if you have reverse flow through the pump. So here, when that valve closes, we want the pump to trip. So what I'm going to do is I'm going to click on possible to potentially allow my pump to trip. And I'm going to uncheck that box right here. And I'm going to do a pump transient. And it's going to trip with inertia. And I'm going to do an event transient where I want my pump to trip when my valve CV gets to be a certain level. So when my valve CV, which the fully open was 100, when it gets to be a CV of 150 or less, this is when I want my pump to trip. All right, and so need to put in a rated pump speed, so we'll say 2544. I'm going to estimate some pump inertia. There we go. So when I trip my pump, it's going to spin down naturally based upon the inertia of the fluid, the motor, and the impeller. And we're going to see what this looks like. I'm missing some information. I need to pick a 4-quadrant data set. This new pump window is completely different, by the way, than it was in Fathom 7. And so it's been dramatically enhanced to really make it a lot easier to figure out what type of specific speed you have of your pump, so you can select an appropriate 4-quadrant curve and stuff like that. I'm still missing something. Event value. Okay. 150. There we go. Now Impulse is happy. All right, so I'm going to go ahead and run my simulation. So the valve is closing. Once the valve gets to be less than or equal to a CV of 150, that's when my pump is going to trip. So this is almost done running. There we go. Critical warnings. So now we can see that we've got some major issues here. We've got extensive amounts of cavitation. We have a specific or a 4-quadrant curve data set that is not matching everything. So let's take a look at what's going on. If we look at the event messages, the pump trips very quickly. It shouldn't be doing that. Oh, you know what? I know why. I was thinking that this was a value of 1,000. I want my pump to trip when my valve gets to be less than or equal to a CV of, we'll say, 30. There we go. Now let's rerun it. So it's getting there. Perfect. And there we go. So when does the pump trip? The pump trips at 21 seconds. So here, if I right click on my pump, I can do a pump speed graph, and you can see here that initially it's operating at 100%. And then once it the valve gets to be less than or equal to 30, that's when my pump trips. So this is how the pump speed decays. Now look at what's going on here. The pump is spinning backwards, and spinning backwards more and more and more. So what's really going on here is when this valve gets to be fully closed, which this is what I've specified, when this valve is fully closed, you're actually going to have potentially some drainage back through the system. So I did not put a check valve on my pump. You could put a check valve on your pump, and that way it'll close and it'll prevent any reverse flow. So here, the reason why it looks like my pump is spinning backwards so much in my pump speed graph is because I do not have a check valve there, so I'm going to have reverse flow. In reality, my pipe is draining, but here, Impulse is going to model that unless I open up the pipe here and I do a special modeling of a partially full pipe. And so that's a way that you can see how the pipe could drain, and that would be a problem. And so let's see what's going on in the whole system. So if I do my animation again, I'll select those pipes and I'll do my profile. So I'm going to look at both pressure as well as vapor volume. I've got cavitation I'm having to deal with now. Nothing happens very much until the valve is getting pretty close. So 21 seconds. So that's when we'll run. So here, my pump is tripped. So let me back this up a little bit more. So 18 seconds. All right, so here's what's going on. The valve is closing, and as the valve closes and the CV gets to be CV of 30 or less, that's when the pump is going to trip, which upstream you'll see that decrease in pressure. So now as the pump trips here, you can see that you have a decrease in system pressure. That valve is still closing, but it's not closed all the way yet. If this system pressure decreases to vapor pressure, that's when you're going to start to see cavitation and vapor bubbles forming. And then this is where you start to see a lot of chaotic behavior due to cavitation. So there's a lot going on there that you really have to look at carefully when you're using AFT Impulse. So on that note, let me finish with just a couple more points here. So you can see now how things are completely different when you're doing a Fathom XTS transient simulation versus an AFT Impulse transient simulation. XTS is long-term, long, slow transients. Impulse is very short-term, fast transients. Impulse is more of an art than it is a science. There's not a lot of black and white like it is for steady state. So be sure that you educate yourself on how to use Impulse properly. The reason for it is because there's a lot of gray areas, especially when you start to see cavitation. It requires a lot of care to ensure that you're analyzing your results properly. So in the presentation that I've included for you, here are some really helpful links that I would highly recommend you take the time to watch if you are going to be using AFT Impulse. So here I've listed the quick start video tutorial for Impulse. That is necessary. All of these videos are really useful. These are new feature videos for Impulse 6, which highlights how to use the advanced graphing capabilities of Impulse, which are incredibly powerful and useful for effectively analyzing your Waterhammer and your simulations. In addition to that, these are several webinars that I did last year, all on Impulse with simulating Waterhammer. So those are key webinars where you can learn additionally how to effectively analyze your results. So I didn't spend as much time on how you do a Waterhammer analysis with Impulse today. That's where you'll want to look at these webinars right here. I go into a lot more detail in those. Also, we have our training seminar. So the best thing to do to really learn Impulse properly is to make sure you come to a training seminar. So if you go to our website under the Learning Center, you can find training seminars. We host them at our facility in Colorado Springs, Colorado, 3 times a year. And you can get more information here. We can also come to your location. So if you've got multiple users, maybe at least 4 or 5 users of Impulse or more, we can come teach a training seminar at your facility, and that'd be more economical rather than sending all of your users out to our training seminar here in the Springs. All right. Well, thank you very much, everyone, for your time. I really appreciate it and hope that you were able to see how easy it is to import your Fathom model into Impulse. That way it saves you a bunch of time from the get-go. That way you don't have to build your system from scratch when you get it into Impulse. That way you can do your Waterhammer analysis. If you have any sales-related questions, feel free to email us at sales@aft.com. If you need some tech support or help on a model that you're working on, email us at support@aft.com. And then if you were listening in on the recording of this webinar, feel free to email me at benkeiser@aft.com. I'll be happy to send you a copy of my presentation. Thank you very much, everyone. Take care and have a wonderful rest of your week.